And it gives me great pleasure to introduce Filip Wudarski from USRA and NASA. And Filip will be talking about the nice work he's been doing towards the Fermi-Hubbard model using application-specific annealers. Over to you, Filip.
Yeah, thank you, Paul, for this kind of introduction. So my today's talk will focus on, I guess, slightly different approach to annealing theory than we usually know from past research, and namely we're trying to propose some sort of new way of constructing devices, which we test here numerically mainly with some theory underlying. This is a joint work with here folks written down, and the main part of the work has been done by Ryan Levy that I think is also present in the audience. So also if there is a broader discussion, I guess he'll be also happy to answer some other more technical questions related to simulations. So like I plan to tailor my talk that first I will motivate why we are interested in this application specific annealers and why Fermi-Hubbard model might be this particular instance of this application, which means that I will have to first introduce some notion of Fermi-Hubbard model to the audience that maybe is not too much familiarized with the notion, and how to map this to some quantum computing platform. Having that, we can go next to annealing protocols, and by this I mean like how to model our protocol such that we may expect to achieve some sort of good results if we had the access to this theoretical ideal device. And this will be supported then by the results, not only on the Fermi-Hubbard model, but also on spinless models with some special type of interactions. And finally, I will briefly discuss some comparison of our theoretical approach with the near-term gate-based approaches, and why we think that this might be an interesting alternative for maybe investigating or trying to construct such devices, and also what sort of experimental perspective we may expect in order to implement that. And finally, obviously, I will conclude and provide some challenges that are necessary for further development of the theory, and also how to relate that with the experiment. So let's start with the motivation. And here I provided like a very brief and high-level description of what is quantum annealing. And quantum annealing is like a paradigm that aims to solve classical optimization problems. And what I mean by that, I try to emphasize that classical is not necessarily the key ingredient of quantum annealing, but because we have access, or D-Wave has popularized quantum annealing as a computational paradigm, and they use classical Hamiltonians. This is why usually we think about annealing in terms of classical problems, or in other words, as using Hamiltonians, or that can be related to cubo-quadratic unconstrained binary optimization problems. This is some sort of limitation, but also you can find different problems, even NP-hard problems, that can be mapped to cubo problems, and therefore to annealing problems of using Hamiltonians. And then what is optimization in this scheme? Optimization is that if we think about a problem and we want to encode this in some sort of Hamiltonian, we usually think about our solution to be the ground state of that Hamiltonian. And we try to exploit features of quantum evolution, namely an adiabatic theorem, and how this evolution can help us in finding near the ground state, or ideally the ground state, which means the solution of that problem. And this paradigm has been around for more than a decade now, and we've witnessed different applications from machine learning, sampling, traffic optimization, plenty of very flashy titles and problems. However, still it's unclear if we may expect quantum speedup only within the QUBO realization, implementation, and this sparse connectivity that is offered by D-Wave. So, like the very interesting question is like, can we use D-Wave architecture or this classical Hamiltonians to encode something that is of quantum way, which means that's not only a classical Hamiltonian, but maybe something more quantum. And yes, there are like approaches that exploit so-called gadgets or some fancy implementation, mappings. However, it's not native, and understanding possibility of experiencing quantum speedups in that systems is even more complicated than even trying to figure out a system, classical system, where we might expect quantum speedups. So this is why we try to tackle problems that are manifestly quantum. And the question here is, where is it more likely to expect quantum speedups? In problems that are classical, but exploit some quantum effects, or in problems that are natively quantum and still exploit quantum effects, and therefore maybe it's the quantum advantage is there. So also related question is if the quantum gate or universal fault tolerant approach is the best one and the only one. Is it the only one that the general broad community should pursue? Or maybe it's better to not place all our eggs in a single basket, but try to maybe explore some application-specific platforms, different architectures, different approaches like annealing, maybe not kind of adiabatic universal approach, but maybe only application-specific annealing. And then what are the promising problems? And here I will try to argue that Fermi-Hubbard models might be this sort of promising problem, and we'll try to propose also some sort of architecture that is needed to solve them. And by architecture, I mean what sort of interactions or couplers are needed to be implemented, what sort of state preparation procedure is required, what sort of measurement protocol is required in order to implement some sort of specific application-specific problems. So having said that, let's go to Fermi-Hubbard model. This is just a brief overview of the problem. Just as a reminder, like Fermi-Hubbard is a proxy model for some material simulations. We can investigate some insulating phases, superconductivity, and other properties of materials on different level, not this low level of molecular or atomic level, but instead we are focusing only on electrons hopping between lattice sites. And this model is composed of a couple of terms, like terms that are related to hopping of our electrons from site to site. We can have either spin up or spin down electrons that hop, that are destroyed on one side and then created on the other side, as well as we have on-site interaction that is characterized by this term. And this is responsible for repulsive forces on site, that if electrons are occupying this part, then they will experience some sort of repulsion due to the nature of electrons. And this model is manifestly expressed with fermionic operators, which are not native to standard orthodox way of thinking about quantum computers, which means that we'll need to provide some sort of mapping. The other model that is very closely related to this one is this Hamiltonian TV model. Like if we have only this part, it is called tight binding model. Here we are introducing another interaction term. And the key difference is that we neglect existence of spin. So there is no Pauli exclusion principle. We have only a fermionic particle that can either occupy or not a given site. So since this is not a native way of implementing some sort of quantum fermionic Hamiltonian on a quantum computer, it's worth also mentioning that each site can be either occupied or unoccupied by a spin particle, spin up or spin down, which means that we may think that, okay, so maybe we could associate state 0 with unoccupied site and state 1 of our qubit with an occupied site for both spin up and spin down particle. And this brings us to the Fermion-to-qubit mapping. So the methods how one may translate fermionic creation and annihilation operators into some Pauli, let's say, operators that are more native to our orthodox quantum computers. And there is a fair amount of different encodings. Every single encoding has some pros and cons. Probably Jordan-Wigner is one of the most commonly known and exploited approach. The key advantage is that you're directly mapping your Hilbert space of fermionic operators, Fock space to the Hilbert space of Pauli operators, let's say, that are easy to interpret in the sense of occupation and without occupation. However, the key disadvantage here is that the operators that are the fermionic operators are not local within this transformation. So we would need to have very long chains of Pauli operators, which experimentally are difficult to implement as the dynamical feature of a device, but it is easy to extract in some sort of more proxy way on a gate-based computer. In this talk, I will focus on the very last encoding, that is low-weight encoding, recently proposed and very promising encoding. And the key advantage here is that on the expanse of trading of kind of locality for the number of qubits. So this is the way that this encoding works. And here I displayed two ways of mapping, like let's say two problems that we'll be going to discuss here. One is for the spinless particles and the spinful particles. And the spinless particles are easier to discuss. The spinful particles are easy extension to that. And the encoding, this encoding works as follows: that with our lattice, that okay, there is like some limitations with the shapes of lattices that you can employ this encoding, but for this purpose, we'll focus mainly on square rectangular lattices here, which are applicable with this encoding. So with this encoding, you're introducing directionality of our lattice. So previously we had like only hopping between the sites. Here we are additionally introducing edges with some directionality plus extra qubits. And this allows us to encode our creation and annihilation operators with the given edge and the vertex operator. And the edge operators are up to, at most, Pauli weight free, so free local operators, where xi are given by the edge ij. So let's say, like, if this is I and this is j, this is my edge ij, and f here represents the auxiliary qubit. So in this case, it will be this qubit. And from the perspective of potential experimental realization, this is way better than having order of the total size of the lattice. So here we are limited only to, at most, Pauli weight free, which gives us also the motivation for our work here, since this is something that is maybe not currently achievable, but very close to realization. Therefore, it might be interesting to pursue this direction. And here are like some ways of encoding all the terms that are present in the Fermi-Hubbard model, which means that you see that we have some combination of Pauli weight-free operators with x, x, and y on the extra qubit, or triple x's, or y, y, x, y, or triple y's. So these are the only terms that appear in the Hamiltonian, plus the on-site interaction with the fairly trivial Z interactions. Additionally, since we're introducing extra degrees of freedom in form of extra qubits, we are expanding our Hilbert space. The Hilbert space is not necessarily matching the degrees of freedom in the Fock space. Therefore, one needs to introduce also a stabilizer formalism that is related to understanding what are the states in this physical larger Hilbert space that correspond to the logical states in the Fock space. And this is achieved through introducing this sort of stabilizers that are at most Pauli weight 8 with Z terms on these qubits, on these qubits, and x or y depending on the orientation. X in the vertical, horizontal, sorry, and y in the vertical way. And this allows us also to exploit some notion of error correction, maybe not full, but some notion of logical space. So now, if we have our Hamiltonian from the fermionic Hamiltonian mapped to the qubit with Pauli operators, we may ask a question: can we perform annealing scenario, annealing procedure to arrive to the ground state of that Hamiltonian? And what is needed then? What extra ingredients we need? We need the initial state, and the initial state will be given by the ground state of the driver. We need some sort of dynamical features in form of the schedule. And what else? Can we benefit from this encoding? Namely, can we benefit from the fact that it has this logical / error correcting structure? And finally, how to prepare the initial state of that Hamiltonian, and how to measure final answer. And these are the questions that I will now try to answer. So first, we have investigated different types of our driver, our initial Hamiltonian, and we found out that arguably the best way of approaching this is by introducing so-called a checkerboard pattern Hamiltonian. And by checkerboard pattern, I mean that it is fully local Hamiltonian of this form, with Z operators on every single main grid side with different sign. The plus sign will correspond to these qubits, and the minus sign will correspond to highlighted qubits here. Also, the number of minus signs will depend on the problem that we are trying to solve. So since the Fermi-Hubbard or the tight binding spinless problems are particle preserving problems, we may exploit the fact that our final Hamiltonian cannot increase nor destroy particles that are initially or that we try to understand our problem. Therefore, this driver also preserves, starts with a given number of particles that we try to investigate, and it exploits that that fact, that sort of symmetry, which means that the Hamiltonian, the total Hamiltonian, commutes with the number of particles Additionally, this driver also commutes with all stabilizers, which means that this driver cannot drive us from the logical space outside of it. And this is interesting and important feature of that model, because even though the encoding gives us this logical and physical space notion, the true ground state of the encoded Hamiltonian, which is not necessarily its logical one, might be lower in energy than the logical state. Therefore, imposing this symmetry of preservation through this commutation, it will allow us to stay in the logical space and not relax to the non-logical state. Additionally, mainly we will focus on this sort of local form. However, we also looked at so-called non-local or full drivers, where we additionally looked at most Pauli weight 4 Hamiltonians with the terms of the driver living on these extra qubits, and we'll try to argue that it is not necessary to consider this sort of high Pauli weight terms. Then comes the state preparation, and the state preparation will also be related to the problem that we try to aim. So if we plan to have, let's say, as here demonstrated, 4 particles living on this Fermi-Hubbard lattice, we will have 4 terms here. S here indicates the squares, and W indicates white dots here. And then there is additional term that is related with this, with all the auxiliary particles present in the encoding. And this is probably one of the bottlenecks of, at least current bottlenecks of our approach, that we know that this state can be easily, efficiently prepared on a gate-based computer, but it's unclear how to efficiently and reliably prepare it on this proposed annealing structure. What about the schedule? So in our work, we mainly focus on the most trivial schedule, the linear one. However, we also looked at the schedules that are currently used in D-Wave 2000Q and D-Wave Advantage, just as some sort of non-trivial extension of the model. However, the results already for the linear schedule are quite promising. And the final part of the protocol is the measurement part. And the measurement can be split into 4, maybe 5 measurements that are local in terms of measuring independently X, like some sort of combination of X, XX, Y, XXX, and so on the main qubits, and some different operators on the auxiliaries, plus the trivial Z measurement on all qubits. And from that, you can stitch together and infer the expectation value of your Hamiltonian. So now here are our first results that somehow justify the reason why later we stick only to purely local terms. And this is for the spinless case. We started with the spinless case because it's easier. The dimensionality is smaller, therefore we can access larger lattices or higher dimensional Hilbert spaces. So we can simulate more systems and understand statistically better properties of that, and based on that we'll infer that the sort of arguments are transferred also to the spinful systems. So as you see, we have investigated quite a number of different system sizes for 2 electrons and 4 electrons living on different lattices. where the bars are giving us information about the mean value of energy that we can, the mean value of this difference energy of the state that we arrive with the end of our annealing time. Here we operate in unitless arbitrary units scenario with total annealing time being 100, with T and V being set to 1, and we are checking what is the value, or like how close to the true ground state are we after the annealing, with the standard driver as this local driver without any terms on the auxiliary, or with all, which means also the driver with the terms on the auxiliaries. And note that terms with the auxiliaries can be of Pauli weight 4. And this is something that ideally experimentally we would like to avoid. We don't want to go beyond Pauli weight 3. This is also our kind of argument for this application specific annealers, that we want to keep our interaction terms that would need to be implemented or hardwired in the potential device up to Pauli weight 3. And this graph demonstrates that yes, for some instances, it is more beneficial to have all terms, but on average, it's not always the case, and which suggests that, okay, maybe if it's much more way more complicated to implement them or to realize them experimentally, why even to bother and keep them? Therefore, further will only restrict to the local drivers. The error bars are demonstrating the mean and the minimal and the maximal value over different arrangements of our driver. So if we, let's say, if we go back here, if we fix our number of particles for this lattice to 4, this is not the only way that we can arrange them. We can think also about, let's say, this one, this one, this one, and this one. And this arrangement will definitely lead to different dynamics, but also may lead to slightly better or slightly worse results. Therefore, we scanned through all of the available possibilities that are unique and investigated this in more statistical manner. Therefore, here we report only the mean value and then the minimal and maximal value between them. Also, what is interesting from that plot is that quite crucial figure of merit for, let's say, some sort of difficultness of our problem in annealing is the energy gap. And what happens in most of the cases here, and also I will show you this for spinful systems, is that the energy gap, the minimal gap, is either close to the very end of our annealing, or it's not substantially different than at the end, at the spectral gap, which means the difference between the true logical ground state and the logical first excited state, which means that our schedule is such that the gap is going to the point where at the end is close to the smallest. Like for this scenario, this scenario, this scenario. For some others, it is slightly different in other place, but it's not, you know, like exponentially smaller than the spectral gap, which might be promising from, let's say, scaling perspective, but the scaling perspective is also something that is very difficult to identify in kind of decisive way. Additionally, you see that from that graph where we, instead of looking at the average values over all the collected data, we looked only at the best selected driver. you see that the dots here are without the auxiliary, which means fully local driver, and the triangles are with the auxiliary terms. And from that graph, you may say that, okay, it's sometimes it's better, sometimes it's worse. So let's don't focus on them, because engineering of these sort of problems might be more complicated. I see
Filip,
that there is
something in the chat. Yeah, something in the chat from Lorenzo, who says, "Can I ask how you perform the numerics?"
Thank you, Paul.
Yes. Okay. Yeah. So numerics here are performed like we try to simulate the full annealing scenario in the logical space. So since we know that the symmetries allow us to restrict only the Hilbert space to a given sector number of particles plus to the logical subspace, we don't need to bother about some sort of possibility of leakage. So we can restrict our Hilbert space to smaller dimensionality subspace and perform there the entire evolution. And this is like a full Schrödinger equation solver with Q-tip. Is that satisfying, or there is some follow-up to that?
Yeah, thanks. That's very demanding. But how do you integrate actually Schrödinger equation? Just not, one Euler step, or Runge-Kutta fourth order, or something more exotic?
So I don't remember precise the details, but we used Q-tip Schrödinger equation solver. I don't know what is the back engine of that. And I don't also remember the full how many steps points we include in our simulation. So like in general, we fix the total annealing time to this 100 units, and we divided into some small steps and perform the integration of them. I don't remember the precise integration method there, but this is like from Q-tip Schrödinger equation solver.
Okay, thanks. So the ground state, you get it with some Lanczos method.
Yes.
Okay,
yes, we can do full diagonalization here for this problem, so we can easily compare it.
Great, thank you.
Yes, so so having this sort of promising, or not necessarily results that are not necessarily giving us information that, oh, you need definitely this Pauli weight 4 terms in the annealing for spinless particles, we decided to keep only local terms, which is from the experimental perspective even better, but also from the numerical perspective, we may also neglect some degrees of freedom here. And therefore, for now, jumping to the spinful model, we only focus on local Hamiltonians. And for spinful systems, when we fix the number of particles, we need to fix the number of particles, let's say, of spin up and spin down. And this gives us also a couple of different possible arrangements, in the sense that previously we had, let's say, only 4 particles to set on the lattice to distribute them. Now we have different number, not necessarily different number, but we have spin up and spin down particles, and we can use our checkerboard pattern either in the way that the initial configuration is matching, which means that a given side is occupied by spin up and spin down, or that they start on different lattice points. And this is like what we call matching, when both particles spin up and spin down occupy one side, and different means that they are not matching. That's let's say in one corner we have spin up, in other corner the spin down particle. And this is 4x3 lattice, the largest lattice that we have investigated here. And as a function of U and T, that is a relevant figure of merit for Fermi-Hubbard models. And we clearly see a drop in performance for large U by T, which might be related with the fact of if U is large, then it means that this term is dominating. And this term is composed of Z operators. And our driver is also composed of Z operators, which means that up to some first order approximation, our Hamiltonian commutes with our driver, which means that we cannot induce, or we are mildly inducing the dynamics, which is the reason why we additionally inject some additional terms to the Hamiltonian that are commuting with the with that part and allow us to explore the Hilbert space more efficiently. So this is without the green, this one is with this additional term or Heisenberg term, we call it XX plus YY on some auxiliary qubit. And this allows us to improve slightly results. On the other hand, this also increases locality of our driver. From one local locality, we are moving now to 2 local Hamiltonians in the driver, which arguably is not a big problem, but this then boils down to some potential engineering problems of implementation. Moreover, here as well, the gap is minimal at the close to the end of the evolution, which means that during our, at least with this linear schedule, during our close to adiabatic evolution, the gap is fairly big and is only getting smaller up to the value of the spectral gap, which is also nice that it's that we do not experience some sort of very exponentially small gaps in the middle of the annealing. Additionally, we also looked at properties of other local observables, or in general observables, local and non-local, spin and charge observables, local and non-local, and for the spin as well, local and non-local. And also the error here is quite small, which is interesting from the perspective, in a moment I will, yes, I will tell you something more about this, but it is interesting that this protocol gives us a state that is close to the true ground state, and is not only optimizing with respect to the energy value, but we can also extract relevant figures of merit like other observables with greater confidence than otherwise if we were only to optimize with respect to the energy. And this gives us this nice segue to the comparison with the gate models. And we used mainly two papers for this comparison. One paper focused mainly, and this is also for the near-term architectures, which means VQE variational quantum eigensolver methods. One is more theoretical based on the resource estimation and how much time one would need to perform the optimization with the gradients, the computation of the energy plus the computation of the gradients, and with some maybe not guarantees, but some sort of promises of maybe convergence near the ground state. and that would be on the order of 10 to 5 seconds. The other experimental paper recently appeared in Nature Communication. This is work of Facecraft and Google. They focus on smaller lattice, also VQE with different optimization scheme, only a single layer with only 4 parameters. However, they have arrived near the ground state with the error 10 to -2, which is quite good for this particular model. And the total time is 10 to 3rd, with the caveat that in this paper, they take always 40,000 samples for everything, for the optimization and then computation, final computation of energy. Here they vary the number of optimization shots, only 1,000, and then for the final energy estimation, 100,000 shots. And in our case, we take numbers from currently existing annealers, which means D-wave, and we take, let's say, the same number of samples, and we argue that since we have in total 5 different measurements, these 4 triangles that I showed you, plus the ZZ measurement, so we need to run 5 times each annealing, and the total time will be the time of the annealing, the time for the reset, and the preparation. And this will be depending if we take the lower values of the D-wave schedule or the highest, something between 100 seconds to 50,000 seconds. So it's comparable, though the details are necessary for an appropriate comparison here. But the key point here is that it is at least a promising alternative for the near-term computers. Every single method here has its own caveats, like here I haven't included any sort of error correction mitigation strategies, no noise, nothing based that we can solve it. Here there are some overheads for the error mitigation, but also the scalability of the system will affect. Like if we go higher in the lattice size, it will mean that there are more layers, more parameters to optimize, and additionally, no theoretical guarantees for arriving near the ground state. Here, this method seems to be size independent, in the sense if I have had access to a big annealer, then I don't care if I run only 5x5 lattice or 10x10 lattice. Like there are no additional parameters that are dependent on the system size. And finally, let's go to the experimental perspective. And I guess that this is also related to this commercialization by D-Wave and promotion of quantum annealing. But so far, we've been mainly focusing on like local X or Y or Z interactions plus ZZ interactions if two local interactions. However, this clearly limits us only to this classical optimization problems. Currently, there are like other actively investigated paradigms of implementing 3 local Zs, 4 local Zs, which would enhance the performance for the classical optimization problems, but may not necessarily be suitable for our current purposes. And there are active research on the Josephson phase sleep qubits that can promise or might be a promising path for implementing terms like XXX, XXY, and so on that are present in our annealing Hamiltonian, Fermi-Hubbard Hamiltonian. Therefore, this gives us some sort of hope that if somebody is interested in pursuing application-specific for the Fermi-Hubbard models annealing paradigm, then there is some promising tech that needs to be obviously developed, but at least there is some path towards a realization of them. And finally, let me conclude that Fermi-Hubbard, especially in this low weight encoding, are kind of a promising platform for the application specific. And first of all, Fermi-Hubbard models are interesting problems from industrial or real world problems applications. Second, there might be easier to achieve some sort of quantum advantage, quantum speedups, because they are very difficult to classically simulate. And going, let's say, 10 by 10, 100 qubits could already be something that is not feasible for classical simulations. However, there are plenty of different challenges here. I haven't discussed any sort of noise. We looked at specific coherent noise type that our protocol is fairly robust against that, but more disturbing sort of noise is all sort of decoherence and especially leakage from our particle sector or logical space. Therefore, this definitely requires more investigation here. State preparation, as I mentioned, is easy on the gate base for that model, but it's unclear how to do it clearly and efficiently in the total annealing scenario. Scaling analysis here is additional caveat that we went arguably as far as possible in the simulations, what is possible to do. However, this doesn't tell us that, you know, like if we go to 10 by 10 lattices, the gap might shrink exponentially and all possible annealing or close to adiabatic evolution is infeasible, or you need to evolve for eternity. And then obvious problem, experimental realization. We have the proposals for some sort of approach trying to achieve that, but this is not enough. Like we need experiments, we need platforms, and probably if we start realizing them, we'll find out that this is just the tip of the iceberg, and the number of problems is way greater than we initially realized. And with this, thank you for your attention, and yeah, please ask some questions.
Great, thank you very much, Filip. Lots of interesting ideas there. Thank you very much. Are there any questions from any member of the audience for Filip?
Hello.
Evgeny, go ahead.
Yeah, thank you for the good talk. I want to make sure certain things that I may have missed. So the vertex operators in your Hamiltonian definition slide, they were never defined, but they're also less than 3 local, right?
Yes. So vertex operators actually are just Z operators. Like, yeah, I didn't want to go to the details there.
Great. So, and this works only for the square lattice?
There are a couple of different realizations, like hexagonal lattices and even Kagome lattice, I guess, is possible to realize. The papers of Darby and Klassen, the initial one introduced this for square and hexagonal, and then they expanded for different lattices. Yeah, so kind of some number of lattices, but not arbitrary lattice.
So then when you plotted delta E, that was after annealing for 100 units of time with your simulation. So, and that's the state that you got. It was this close to the ground state, right?
Yes, precisely. And we looked both at the energies and fidelities, because also you can imagine that, you know, you have like a very close in energy, but you only flip 1 qubit, let's say. This gives you 0 fidelity because they are orthogonal, but in energy they are close, but also yeah, so we looked on both type of quality figures of merit here. I demonstrated the different figures for spinless and spinful, but yeah, in general, we have some intuition about the quality.
Thanks for this quick answers. I just wanted to bring up, since you mentioned the classical simulation, there was this recent paper by Garnet Chen. I don't know if you have seen it, but he makes really bold claims about classical simulations having really easy time with problems like this. And essentially, there are, of course, 10 by 10 grids where you can come up with a Hamiltonian that classical simulation can choke, but on those, the gaps will also be really small for this quantum annealing path. So that's his broad kind of big picture statement.
Okay, cool, thanks. Yeah, can you type a name or a paper reference in the chat? That'd be really nice.
Okay.
Any further questions for Filip?
Maybe I have a question. I frankly forgot about the phase diagram of the Hubbard model in 2 dimension, but I think I saw a picture of the gap. So you're saying basically that the system is always in the same phase for the parameters that you've been looking at?
So here we haven't investigated phase diagrams in the sense of you know, like altering parameters, yeah, like in the sense of altering T and U parameters during the evolution. With our modus operandi is we fix T and U and we perform the full annealing. We don't change them during the evolution.
No, sure, but since it performs, I think you said it yourself that it performs worse for larger U. I was thinking that maybe you're entering another, you know, there's a phase transition, or you know, the state changes essentially, and basically you're getting very good results because you know it happens that your driver, your initial state is a good guess, but then it may not be a good guess for larger U. I don't know. That's just a.
Yeah, so I don't have an answer to that question. We haven't investigated this more carefully. Maybe Ryan, if you can, if you want, you can chime in here, and maybe you have more intuition here.
I mean, for large U, you should enter some Mott insulating thing. I mean, I guess.
Yes.
I think Ryan is no longer on the call, Filip. So.
Okay. Yeah. No problem. No problem.
There's another thing that I remembered, which is, so in cold atoms and trapped ions, kind of quantum simulators that people build nowadays, they can actually have fermionic atoms or ions, so they can directly, if you will, simulate Hubbard model. So how does your scheme compare to that?
We also haven't compared that with, you know, like native fermionic computers, like that sort of work aimed more into understanding if quantum annealers of this sort of natural standard way can be a promising platform for solving some non-trivial Hamiltonians. And yeah, I guess that it's also not easy to think about some non-trivial Hamiltonians that are readily related to some applications. You know, we can talk about whatever Heisenberg models and engineering Hamiltonians that are non-classical and discuss the properties of that, but it was more to investigate something that has easy and tangible relation to applications.
Any final questions for Filip? Okay, if not, let me thank Filip once again on behalf of everyone in the audience today. Thank you very much, Filip. Very interesting talk. Lots of interesting ideas. I look forward to meeting you at the INQA conference in a couple of weeks where we can talk about this in more detail. But until next week, I wish everyone a safe and productive time. Thank you very much. Thank you, Filip.
Thank you, Filip.
Thank you, Paul. Thanks.
Good. Cheers, Filip. I'll stop the recording, which I've forgotten to do.
Yeah, thank you.